Welcome back, students. This is the theorem what I suggested you to prove. So I hope you have done that. So let's go and prove this systematically. Let me go to the next page. First one, proof. Okay. Now first, we have to show that X and empty sets are closed. That means you have to show that the complement of these sets are open. Okay. So since complement of X is empty set, and since tau is a topology, that implies empty set belongs to tau. This implies X difference X is open in X, and this implies X is closed in X. This is as simple as that, right? Now again, since you take empty set, remove you take X, you take the complement of empty set. The complement of empty set, X difference empty set, will be equals to whole of X, because we are not removing anything from X. And we know that since tau is a topology, X belongs to tau, that is X is open. This implies X difference empty set is open in X, and this implies empty set is closed in X. Done. Just 4-5 lines. Okay. Second point says, if A and B are closed sets in X, then their union is closed. You have to show. So let me write. Let A and B be closed sets in X. To show that A union B is closed in X. That is what you need to show. You need to show that X difference A union B, the complement of union B, is open in X. This is what you have to show. Okay. Now, what is the given data? Your given data is A and B are closed. Since A and B are closed in X, that means the complement of A, that is X difference A, and complement of B, that is X difference B, are open in X. Okay, mark this point. We will use this. Now we have this fact. Now let us check what is this X difference A union B. We have to show that it's open. X difference A union B, what will be this? So of course, if you want to study these things, you should know all the properties, almost all the properties of the set theoretic operations. Now what is X difference A union B? If you remember De Morgan's law, this is nothing but A union B complement. That implies A complement. So X difference A union becomes intersection X difference B. Right? This is by De Morgan's law. So now here X difference A is open, X difference B is open, and we know that the intersection of two open sets is open. That implies X difference A union B is open. Right? Is you write those 3-4 lines. Open in X. This implies this is open in X. This implies X difference A union B is open in X, and that implies A union B is closed in X. Done. This is what we want to show. X A union B is closed, that is you want to show that X difference A union B is open. This is what you have proved, and if this you have proved, then A union B is closed, and that's what your aim was. Third point says, if you take arbitrary collection, then their intersection, that arbitrary intersection is closed. So let us take arbitrary collection. Let A alpha is alpha belongs to I be collection of closed sets in X. To show that arbitrary intersection alpha belongs to I, A alpha is closed in X. That is, we need to show that the complement, that is X difference intersection alpha belongs to I, A alpha is open. The complement of this set should be open, then the given set is closed. So it's open in X. This is what you have to show. Now here, as I said, these all A alphas are the closed set. Use the fact that and use the definition of some operations, not definition, the operation properties of the operations of intersection union. We will get the desired result. Alright. So here now we know that A alpha is closed for all alpha belongs to I. Okay, because you are taking the collection of closed set. This implies the complement of A alpha is open, closed in X. Open in X for all alpha. And this implies the union of open set is open. So if you take union alpha belongs to I, X difference A alpha, this is open in X, because arbitrary union of open set is open. So this set will be open. Okay. Now let us check what is the complement. X difference intersection alpha belongs to I, A alpha. By using the set theoretic properties, this will be equals to union alpha belongs to I, the complement of A alpha, and this is open. Is open in X. Just now we have written that this fact. Hence, X difference intersection alpha belongs to I, A alpha is open in X. Right. Yes. And hence intersection alpha belongs to I, A alpha is closed in X. These three properties. So you check your write-up and see how we have written, and understand or learn the technique of writing any proof. And remember, you are writing the proof not only for you, but you are writing the proof for others to understand. Right? So write it in a proper way. Alright. Now here. Now we have a set X with topology tau. I remember in the last lectures we have defined something called as, you take a subset of X, that is you take a subset of X and you define a set tau Y, and we have shown that it's a topology, right? And any set here is A belongs to tau Y. This is open if and only if there exists some open set U in tau such that this A can be written as U intersection Y. Okay, this you check. Previously we have already proved this. Okay, a subspace topology. Now the question is, you have a set X. I will rub this afterwards. You have set X, and you have subset of X which is Y. You have topology tau on this. You have topology tau Y on this. If you have a set which is open in Y, does that mean that set is open in X? You have something which is open in Y, some set which is open in Y, does that mean that set is open in X? Secondly, you have a set which is closed in Y, does that mean that set is closed in X? Or if not, what is the condition which will tell you directly that if you have a set which is closed in Y, then obviously you can always imply that that set is closed in X also. Okay, so you can answer this question and come back here. Let me prove, or rather proving, let me just state the theorem and you find the answer for that theorem and write the proof of the theorem, and then I will try. I'll do it for you. So let x comma tau be a topological space and let us take Y which is a subset of X. Okay, and let us take tau Y which is a subspace, be the subspace of tau Y with the subspace of let me write on Y. You take a subset A of Y. Let A be the subset of Y. So let A comma A subset of Y is not let. Subset A of Y is closed in Y. That's why I have already mentioned you, right, where it is closed in X or in Y. Okay, a subset A of Y is closed in Y if and only if the same condition what we have for the open set. If and only if there exists a closed set, let me take B, closed set B of X such that you can write this A as B intersection Y. So this is how we define the closed set, or how we can check whether it's closed or not. Okay, so any subset in Y in a subspace topology, if you take, to show that that set is closed, you need to find a closed set in whole space such that you can write this A as the intersection of B and Y. Okay, so let me just give a proof, definition for this. So you have this entire X, this is X, you have a subset of X, let me take a small subset of X, say Y, and there is a subset of Y, say somewhere here. Okay, this is A. Now this A subset of Y is closed in Y, rather I can tell you about open also. This subset A of Y is open in Y if there exists an open set in X such that you can write this A as Y intersection the open set. And similarly you can go for the closed set. This A subset of Y is called closed, is a closed set in Y if and only if you can find a closed set in whole X such that you can write this A as Y intersection that closed set. This is the theorem. Okay, now you may say that you can take the intersection with x because x is always open in x. But you can't do that, because if you take the intersection of y and x, obviously since y is a subset of x, you will get y intersection x as y only, but not a. So you need to find a subset of x, something like this, say u, such that u intersection y will be equals to a. Now in that case, if u is open, then a is open. If u is closed, then a is closed. So you can use both the definitions here. Both will go parallelly. So this says if you can find a closed set in X such that you can write this A as y intersection u, then A is closed in Y in a subspace topology. So again, I suggest you write the proof of this. You take your time. Once you are done, you search for the proof. Rather, you search for the proof, refer your text, refer the reference books, and you come back to see the proof. That's the way you will learn. Okay. So again, see you in the next video.